The rock that is shown in the photo is a piece of tuff, which is a type of extrusive rock.
You can see that the pyroclast and volcanic ash aggregated together. Here is how it was formed.
When there was a volcanic eruption,
ash particles and pyroclasts or rock fragments were created in the surrounding area. They underwent fast cooling and crystallization to form fine-grained minerals. They aggregated and the lava glued them together
in the tuff. However, another situation might happen was that after volcanic eruption,
ash particles and pyroclasts combined with foreign rock fragments, which might be lodes from a river or sedimentary rock. They underwent fast cooling and crystallization to form fine-grained minerals. They aggregated and the lava glued them together
to form tuffite. Here you can see some round rock fragments, showing that it was transported for a long time to the place where volcanic eruption happened. This is a sign indicating that there are some kind of foreign sedimentary materials.
For this photo, some brown stains can be seen on the rock. This is due to oxidation, which is a kind of chemical weathering. Minerals react and combine with oxygen in the air or dissolve in water. Brown stains can be formed when iron oxidizes into reddish-brown iron oxide. Oxidation concentrates on joints as they are the lines of weakness and are more vulnerable to weathering. It will be more serious on the junction of joints. That is why sometimes the brown stains appear as checks.
The rock that's shown in the photo is sedimentary rock. You can see that there are alternative layers in it. Sedimentary rock is made up of materials which are eroded from pre-existing rocks and the remains of living organisms. The loose rock fragments are deposited as sediment and then accumulate. The weight of the overlying materials compress the lower rock layers, and water is expelled out. The sediment will then undergo compaction, cementation, and liquefaction before it becomes sedimentary rock. There is also a situation with the presence of soluble minerals. A layer containing minerals is formed when water evaporates and only minerals are left. This forms a sedimentary rock with alternative layers containing both fine and coarse sediment. This is how sedimentary rock formed. The rock shown in the photo is slump fault. Slump fault will form when there is submarine landslide. When slumps form in poorly consolidated sediments, they commonly undergo faulting, particularly at their leading edges during their emplacement. The asymmetry of the slump faults can be used to determine parallel slope direction in sequence of sedimentary rocks. This is how slump fault forms.
The photo here shows a microfault in sedimentary rock. You can see the discontinuity of rock, and there is significant displacement of layers of materials. Now I will explain the formation of microfault. There may be some heavy materials, for example boulder, that poses great pressure on rock when fell down. A crack may then be produced by the pressure, or there is already a crack existing. The rock under the heavy material will then displace downward, creating a microfault. Here is another photo showing a microfault, where this continuity is clearly shown. The photo here shows a flame structure in sedimentary rock. In the middle, there's a pattern in cross-section that resembles flame. When sediments are not yet turned into solid rock and is in loose and semi-consolidated state, the weight of overlying bed or heavy materials that fell down causes the underlying bed to squeeze up. Usually this happens when both strata are saturated with water and the overlying bed is of higher density. There are some cases that fault occurs in sedimentary rock. As you can see that from the picture, the sedimentary strata are bent and curved. This deformation may be due to an even land surface where sediments deposited. They may also be caused by pressure posed by overlying materials, as recently deposited sediments are normally mechanically weak, so they are prone to deformation.
The photo shows a weathering profile. You can see there are fine regolith in the upper parts and large scorecstone in the lower parts. There are also a thick layer of topsoil on the weathering profile. Now I will explain the formation of this weathering profile. The presence of joints allows water to penetrate deep below the surface, which causes chemical weathering along the joints. Chemical weathering slows down as it gets deeper, because it becomes more difficult for water to make its way down. This results in more angular and bigger corestones nearer the bedrock. The thick layer of topsoil is formed mainly because of landslides, which cover the in-situ bedrock. Therefore, angular large fragments are found in the topsoil. This is a rock showing honeycomb weathering. Here's how it was formed. Wet onshore winds pick up salt from the sea, which seeps into pores in coastal rocks. When water evaporates, salt crystals are left in the pores. They accumulate and grow, which exerts pressure to rock and break off mineral grains or even force cracks to widen. Honeycomb weathering can also be formed because of different rates of expansion and contraction of minerals due to different tidal range, which cause temperature difference.
The rock shown in the photo is cross-faced. You can see that there are some white substances in the shape of face between the rock. Here is how it is formed. First, the rock should be well jointed and is deep underground. It happens when hot underground water with dissolved crust slips into the cracks of the rock and water evaporates eventually. Coarse minerals will then precipitate out. Then, less resistant minerals are weathered and eroded away, and coarse minerals pop up. This forms the significant white face between rocks, which is called crust